Welcome everyone, I am the geeky gamer science teacher, here to help you with 9.2, the gas laws. Solving problems involving gas behavior requires a clear understanding of how physical variables interact. Today, we are going to walk through the logic and formulas needed to navigate these calculations. Every scenario we look at is governed by three specific statistics: pressure, volume, and temperature. Pressure is a physical measurement of the force generated by microscopic gas particles striking the walls of their container. The more frequently and forcefully they hit, the higher the pressure reading becomes. There is one critical rule for these calculations: you must never use Celsius. Because a zero in the denominator would break the math, we convert every temperature to Kelvin by adding 273.15 to the Celsius value. Because these three properties are physically tied to particle motion, changing one variable causes a measurable reaction in the others. These reactions are described by the specific laws we're about to use. Boyle's law describes what happens when the temperature remains constant. In this scenario, pressure and volume share an inverse relationship. As the space available for the gas decreases, the pressure rises. Having a syringe's volume doubles particle collisions, doubling the pressure. Let's calculate. 2.0 liters at 1.00 atmosphere is compressed to 0.50 liters. Using P1V1 equals P2V2, we plug in our values, divide by 0.50, and reveal a final pressure of 4.0 atmospheres. This formula allows us to predict exactly how pressure will increase whenever gas is forced into a smaller container, which is vital for designing safe pressurized systems. Charles' law focuses on situations where the pressure stays the same, but the temperature and volume change. Here, the relationship is direct and proportional. Heating gas speeds up particles. To maintain constant pressure, the container expands. Take a 3.0-liter balloon at 20.0 degrees Celsius, heated to 50.0. Convert to Kelvin, 293.15 and 323.15. Using V1 over T1 equals V2 over T2, we calculate a final volume of 3.31 liters. This thermal expansion is why objects like tires or inflatable structures can change size significantly just based on the outside temperature. Gay-Lussac's law applies when the volume is restricted by a rigid container. In this case, temperature and pressure are directly linked. Because a rigid container like a pressure cooker cannot expand, the extra kinetic energy from heating has nowhere to go. The particles strike the metal walls with increasing force, causing the internal pressure to climb. With a sealed container at 0.80 atmospheres and 300.0 Kelvin, heating the system to 450.0 Kelvin increases pressure. Using P1 over T1 equals P2 over T2, plugging in 0.80 over 300.0 equals P2 over 450.0 reveals a final pressure of 1.20 atmospheres. This scaling effect is why sealed items, like aerosol cans, carry warnings about exposure to heat. The pressure inside will continue to rise as long as the temperature does. When pressure, volume, and temperature are all changing at the same time, we use the combined gas law. This merges the previous three relationships into a single master formula. Before you calculate, rearrange the variables to isolate your unknown. This algebra-first approach helps keep the units organized and prevent simple calculation errors later in the process. Additionally, if any single property remains constant during the change, you can simply remove it from both sides of the equation. Test a multivariable change. A 4.00-liter container shifts from 1.50 atmospheres and 27.0 degrees Celsius to 2.00 atmospheres and 77.0 degrees. After converting temperatures to Kelvin, we rearrange the formula to isolate V2. Crunching the numbers reveals a new volume of 3.50 liters. This combined approach gives scientists a way to model complex environments where multiple physical conditions are shifting simultaneously. You now have the formulas and the logic needed to address standard gas behavior problems across a variety of scenarios. Keep in mind that these laws assume the amount of gas, the number of moles, remains constant throughout the process. We're diving into an epic chemistry quest today. Forget those dry, boring lectures, okay? We're going to treat the gas laws like a video game. We've got levels, we've got challenges, and yep, even a final boss. Stick with me, and by the end of this, you'll have seriously leveled up your chemistry game. So, why are we even doing this? Well, have you ever seen a birthday balloon get all sad and shrunken when you leave it in a cold car overnight? Or, seen that warning label on a can of hairspray about not leaving it in the heat? The answers to all that are hidden in the gas laws. You can think of them as the game physics that control the invisible world of gases all around us. All right, every good quest starts with a tutorial, right? You gotta know your character stats. For gases, our three main stats are pressure, volume, and temperature. Get these down, and you are gonna crush every level we throw at you. First up on our stat sheet is pressure, which we'll just call P. So I want you to imagine billions of teeny tiny particles just zipping around, bouncing off the walls of their container. It's like a mosh pit in there. Well, all those little collisions add up, and that combined force, that's pressure. So, if you get more particles hitting the walls, or if they hit the walls harder, you've just boosted your gas's attack power. Simple as that. Next stat, volume, or V. This one's super straightforward. It's just the amount of space the gas has to roam around in. Think of a big container like a huge open world map in a video game, lots of room to explore. But small container? That's more like a tiny, cramped arena for a boss fight. And our final stat is temperature, T. Honestly, you can just think of temperature as a speed boost. When you turn up the heat, you're basically giving all those gas particles a huge energy drink. They start zipping around way faster, which means, they crash into the walls more often and with a lot more force. This one is going to be absolutely crucial, so keep it in mind. Okay, tutorial complete. You know your stats. Time for level 1, Boyle's Law. This level comes to us from way back in the 17th century, from a guy named Robert Boyle, and it's all about the epic showdown between two of our stats, pressure and volume. So here's the main mechanic for this level. The key phrase is inversely proportional. It just means they do the opposite thing. Kind of like a seesaw, If one side, say volume, goes down, the other side, pressure, has to go up, and vice versa. The one catch is that the temperature has to stay the same. The magic formula you need to beat this level is P1 V1 equals P2 V2. Let's make this real. Think about a syringe. When you push that plunger in, what are you doing? You're making the volume smaller, right? You're shrinking the arena. And now all those gas particles are jammed into a way smaller space. They're bouncing off the walls like crazy because there's nowhere else to go. So less space means more collisions, and more collisions mean, you got it, higher pressure. All right, time for a little mini quest to test your skills. We've got a gas at 1 atmosphere of pressure sitting in a 2-liter container. Then we compress it. We squish it down to just half a liter. So what's the new pressure going to be? Well, first we identify our stats. P1 is 1 atm, V1 is 2 liters, V2 is 0.5 liters. We're looking for P2. So we just plug those numbers into our formula, do a little bit of math, and voila! The new pressure is 4 atmospheres. Makes sense, right? We cut the volume down to a quarter of what it was, so the pressure shot up by 4 times. Level 1, complete. Great job! On to level 2, Charles' Law. This one was created by Jacques Charles, and for this challenge, we're going to focus on the relationship between volume and temperature. Whoa, hold on. Before we take another step, there's a super important power-up you have to get. It's not optional. From here on out, for Charles's Law and all the others, you absolutely cannot, under any circumstances, use Celsius for your temperature. It just won't work. The game is coded for Kelvin, so you've got to convert. It's a non-negotiable rule, seriously. Okay, with that out of the way, here's the deal with Charles's Law. This time, volume and temperature are directly proportional. They're a team. They move together. If the temperature goes up, the volume goes up too. If the temperature goes down, the volume goes down. Just think back to that sad, cold balloon. The temperature dropped, so the particles inside slowed down, and boom, the balloon shrank. Let's try another mini quest. So we've got a 3-liter balloon, and it's at a nice room temperature 20 degrees Celsius. Then, we heat it up to 50 degrees Celsius. What's the new volume? So what's the very first thing we do? Come on, you know this. We convert to Kelvin always. Once we've got our T1 and T2 in Kelvin, we can plug everything into our V1 over T1 formula. Do a little bit of cross-multiplying, and the new volume is 3.31 liters. It got bigger, exactly what we expected to happen. You are on a roll. Let's keep that momentum going into level 3, Gay-Lussac's Law. Now we're going to see a duel between pressure and temperature. And for this fight, the arena is a fixed, constant volume. Think of something rigid, like a steel can or a pressure cooker. So just like we saw with Charles's law, this is another direct relationship. They're on the same team. When you heat up a gas inside a container that can't expand, those particles get their speed boost, right? But the walls can't move to give them more room. So what do? They just slam into those walls harder and way more often. So as temperature goes up, the pressure goes way up. And this right here is exactly why you never ever throw an aerosol can into a fire. All right, let's blast through this last mini quest. You've got this. We have a rigid can with a pressure of 0.80 atmospheres, and it's at 300 Kelvin. We crank the heat up to 450 Kelvin. What's the new pressure going to be? We line up our variables, use the P1 over T1 formula, plug in the numbers, and we get 1.2 atmospheres. The pressure went up just as we expected when we raised the temperature. Easy peasy. Okay, take a deep breath. You've cleared all the levels. You've mastered the individual mechanics. Now, it's time. Time for the final boss battle, the combined gas law. This is where it all comes together, because in this fight, pressure, volume, and temperature can all change at the same time. Now don't let this big formula intimidate you. It looks scary, but it's not a new enemy. It's actually just Boyle, Charles, and Gay-Lussac all teaming up into one super formula. This one equation, P1 V1 over T1 equals P2 V2 over T2, it holds all the power of the other three laws combined. In fact, here's a little pro tip. If one of the variables stays constant, say temperature, just cover up the T's on both sides. And what do you have left? P1 V1 equals P2 V2. It's just Boyle's law. Let's do this. Final boss quest. We start with 4 liters of gas at 1.5 atmospheres and 27 degrees Celsius. Then, the conditions change. The pressure goes up to 2 atmospheres, and the temperature jumps to 77 Celsius. We need to find the new volume. What's the very first step? You know it. Convert those temperatures to Kelvin. Then we just carefully plug all our numbers into the big boss equation. We'll have to do a little bit of algebra to rearrange it and solve for V2. And when the dust settles, we get 3.50 liters. And that's it. Boss defeated. And with that quest complete, you did it. You have conquered the gas laws. And you know, in any good game, when you beat the final boss, you get some epic loot, right? Well, your loot today is a set of awesome pro tips. Think of them as cheat codes to make sure you absolutely ace any future homework or tests on this stuff. So here is your official cheat sheet. Number 1, and I'm going to say it one last time, Kelvin. Always use Kelvin. Number 2, keep your units consistent. If you start with liters, you got to end with liters. Same for pressure. Number 3, just remember that all these laws assume you're not adding or removing any gas. The amount of gas stays the same. And here's a real pro gamer move for you. Rearrange the equation to solve for what you're looking for before you plug in any numbers. Trust me, it will save you from so many silly mistakes. So everything we talked about today describes how ideal gases behave. They follow the rules perfectly. But, you know, in the real world, sometimes gases get a little rebellious. They don't always play by the rules we've laid out. So what happens then? Well, that sounds like a quest for another day, doesn't it? Thank you so much for watching. Like and subscribe for more content. That really helps the channel. Also, feel free to leave a comment, any questions you might have or requests for future video topics. And remember, dream big, feed your curiosity, and always lead with kindness.